All right, hello NRF. Today I'm going to be talking about functions. So this is our first step into kind of our new material. Before this, we were of course looking at roots and powers and things like that. So the entire last part of our course is going to be focused around linear functions. And so first off, we're going to step into just the idea of what is a function and go from there. All right, so before we talk about functions, it's really important to understand what a relation is, and then we can describe why a function is a special kind of relation. So, first up, definition. A relation is a set of ordered pairs. Now, it's all well and good to say that it's a set of ordered pairs. But first of all, let's talk a little bit about what a set is. So sets in mathematics are denoted a lot of times. One of the ways to write them down is with curly braces. I'm not very good at drawing curly braces. You'd probably be better off looking in on your keyboard or on your phone, the keyboard that pulls up, looking to see what a curly brace looks like. That's what my random squiggle there on the sheet is. But a set is a list of things that are said to belong together. So this is a set of the numbers 1, 2, 3, and 4. That's what a set is. And so ordered pairs. Now, I don't know really why I broke it up into ordered and pairs. Really, I probably should be talking about it as an ordered pair. You probably are pretty aware that a pair is two things that are kind of put together as a grouping. So in this particular case, when we're talking about the idea of an ordered pair, ordered pairs are mathematically, if we were to write it in a very similar way to what I did as a set, sets involve curly braces, ordered pairs involve round brackets. Both of them have commas that separate the different pieces there. In the case of the ordered pair, it's really important that when we have decided on something that we want to describe ordered pairs for, we do not mess up the order. So that's the ordered part behind the pairing. So if this first number represents something specific, and then the second number represents something different. So maybe this is, for instance, if I pay $1, I get 2 apples. So it's an ordered pair. So it would be, it has to be the case, if I'm talking about ordered pairs, that if I then tell you that I pay I then tell you that there's an ordered pair 2 comma 4, that it's understood that the ordering stays the same. So if this was dollars for the 1, then since it's listed first, it's dollars for the 2. Since it was apples for the 2 to begin with, because it shares the same ordering, the same position, it means that we're looking at apples for what the 4 represents in that particular statement. So ordered pairs are grouping together elements from 2 different ideas or 2 different sets. So this one set right up here, this could be describing, for instance, all of the different amounts of money that I'm able to pay. And so there would be another set that might represent all the different numbers of apples that I'm able to receive. An ordered pair shows you that this element, or this one part of a set, is pairing up with this one part of another set. So I used another word there that's important to talk about, and that is the word element. So an element is one part or one piece of a set. So this setup here has 1, 2, 3, 4 elements. And so if I want to say, well, what is the ordered pair 1 comma 2? Well, it's saying that the element 1 from a certain set, which in my example was the amount of money that I was paying, is paired together with the amount of apples, which belongs to another set. So we're going to talk about this quite a bit more going forward, but yeah, let's fix that up. Probably, as I said, should be listed as an ordered pair. We kind of talked about it all together. There's not a whole lot of point in just saying pairs. You're probably aware of what that means. All right, so quick quiz, even though we were just talking about, get rid of that for a moment. So which of the following statements represents a set? So 1, 2 and 1, 2. The only difference is the round brackets versus the curly braces. So this is, it actually doesn't come up maybe as much once you start getting into dealing with functions a lot. You kind of get away from set notation unless you're describing something we're going to talk about later, domain and range, by using a set notation sort of thing. A lot of times, you're not going to see that as much. So I've given you a little bit of time. If you want to have some more time, pause the video. But the answer to this is that the round brackets, that is an ordered pair. It is 2 elements from 2 different sets. And then the curly braces are showing 2 elements that are a part of one single set. So ordered pair on your left and set on the right. All right, so relations, like we talked about before, are sets of ordered pairs. So sometimes, graphically, one of the ways we organize sets is by putting them inside these little ovals or bubbles. So I have a set on the left of the elements 1, 2, 3, and 4. And I have a set that it's being related to of the elements 2, 3, 4, and 5. If I wanted to write out those 2 sets in the other notation we talked about, I would just do this, 1, 2, 3, 4, curly brace, and then curly brace for the other one, 2, 3, 4, 5. And what this graphical representation of the relation is that 1 relate, well, actually, was that? No, the other way. 1, that's hard for me. I'm going from right to left because of the mirrored thing. 1 relates to 2, and then 2 relates to 3, and 3 relates to 4, and 4 relates to 5. So the idea is that we don't have really a real reason why these things are related. It's just graphically organized, but there's no explanation of why this is happening. But this is a relationship that takes a set of numbers, 1, 2, 3, and 4, and maps them or relates them to another set of numbers, 2, 3, 4, and 5. The second relation looks a little more complicated. And again, we don't have any reason for why this relation is happening the way that it is. But we would have 1 related to 5, and then 2 relates to 5 as well, and 3 relates to 7, but 4 relates to 3, 7, and 9. So if you follow the arrows coming out of the 4 on the left-hand side of our second example there, it's going to 3 and 7 and 9. So the idea is that that relationship actually has more ordered pairs. So for the first one, which I already have both of these sets already written down for, we would have the ordered pair 1, 2, as well as 2, 3, and 3, 4, and 4, 5. Now, one of the things I bumped into that I kind of made a problem of last semester when I did this was I ordered everything for the first example or two. So there is no reason why, for instance, the first one in my list here has to go with the first one in my list down here. It happens for my first example. They actually go those 2 together, and then we have these 2 together, and we have these 2 together, and we have these 2 together. So they all work out just peachy keen, all ordered exactly together. So we have our list of 4 ordered pairs there on the right. If I were to instead do my example that's on the second example right now, I am going to write it all over again just for practice. 1, 2, 3, 4 as being my elements in the first set. And then I have 3, 5, 7, and 9 as being my elements in the second set. But the ordered pairs this time, I have to be careful and follow my arrows. So 1 is related to 5, and that is kind of like this relationship right here. Those two are linked. And then I have 2 is actually going to be related to 5 as well. So I have an ordered pair of 2, 5. I also have 3, 7. And then I have 3 ordered pairs that involve a 4. So it's 4, 3, as well as 4, 7, and 4, 9. And if I go a little crazy with the highlighter over here, I missed the 3, 7, and I also missed the 4, 3, 4, 7, and 4, 9. So something like that. So as you can see, it doesn't have to be like a nice top-bottom sort of pairing there where everything lines up exactly. The elements that are listed in those sets, they can be mixed and matched in any way, shape, or form when we're talking about a relation. So one of the other things is that I've used all numbers so far, but relations technically can be elements of words. They can be elements that just are whatever you want. They could be shapes. So the idea behind a relation is it takes a group of elements and it relates it to another group of elements. Now, this one would be a little more annoying for me to write down the full list of ordered pairs. I'll probably do it anyway. So this is blue, pants is one of the lists of ordered pairs. And then I also have, can't spell, I have blue, shirts, and I have blue, socks. I also have green, shirts, and we have orange, socks, and lastly purple, socks. I just realized if I save these off, that's gonna cut it in a weird way. So I'm gonna put that up there for a moment. Now that is our list of ordered pairs for this particular relation that we're looking at. Again, it's words. It doesn't matter. You could have one of these sets be words, one be numbers, and that would be okay too. So another thing that I bumped into that I forgot to explain very well the first time I did this last semester is that it really doesn't matter how many elements there are in each of these sets as well. So I've done 4 to 4, I think, in all of my previous examples. Well, this is a set of 4 elements and a set of 2 elements. And it's entirely okay to have a set of 4 elements and a set of 2 elements that are matched up like this. And again, my ordered pairs here would be 1, 3, as well as 2, 3, and 3, 4, and 4, 4. So those 4 ordered pairs, those are great. We don't need a list of 4 numbers in either of those sets in order to come up with 4 ordered pairs. Just have 4 arrows or 4 relations between the first 4 relationships between the first set and the second set, the overall thing being called a relation. All right. Now, relations, as we've seen, are really flexible. Basically, they don't really have any rules. They could be numbers, they could be letters, they could be words, they could be shapes. You can go from 1 object to 3 objects. You can go from 3 objects to 1 object. It really, the arrows that connect things can go 2 out of the same one or to the same one. It's really, really flexible. Doesn't have any specific rules that it needs to follow other than being a set of ordered pairs. So each time we've done one of these, as you can see, we've basically just made whatever the relationship is, these sets of ordered pairs. So this right here is a set of ordered pairs, and this is a set of ordered pairs. I'm going to show you sometimes if you wanted to get kind of fancy, you could write it as the relationship is a set of ordered pairs. So you could write down the ordered pairs where each ordered pair is an element inside of the set that you're currently describing. So it looks something like that. Probably won't worry too much about that. I would accept you listing out the ordered pairs that are part of the set, but you can actually put it in set notation itself by putting those curly braces around it as well. All right, so next up we have this particular. Oh, that should be a comma. All right, so in a relation, the set of elements that we start with is known as the domain. So in this particular example, we have this set being the domain, and it's kind of like the starting values. You'll notice that all of our arrows, the ones that I've drawn in, are all one directional. So they kind of have a tip on one end and they have a tail on the other. So you can say, well, this arrow starts here because the tip's not there, and it goes in this direction. So it's coming from this left-hand side and it's pointing to this right-hand side. So what it comes from is like the starting set of elements of the starting set. And we call that specially the domain. This one over here is what we kind of are relating to. It is going to be known as the range. So domain and range. Again, there's no rules as to what can be in the domain or what can be in the range when we're talking about a relation. We can have any kind of randomness relating those two things, and whether it's words, letters, numbers. We're not really getting into anything specifically that way. Instead, we're just saying that if you wanted to refer to one of those sets versus the other set, domain and range are a good, safe way to do that people will recognize. So a function is what we're getting into today, and a function is a special kind of relation. So in a function, it does now have a very, very particular, very specific rule. So it is a relation. So if that's kind of people have trouble with this. So for instance, a rectangle is not a square, but a square is a rectangle. It satisfies all of the requirements for being a rectangle. Now, some people will say that's not true because depending on where you read a definition for a rectangle, it might say that you have two pairs of equal sides that are not equal to each other. But that's, I don't know if that's, depends on who you talk to and how picky you want to get. But if you go with the loose definition of rectangle of two sets of equal sides that are parallel to each other, then squares definitely will do that for you. So you have a set of parallel sides that are equal in length and a set of parallel sides that are equal in length. So squares would fit into the category of a rectangle. But rectangles do not have four equal side lengths that are all parallel to each other, meeting at right angles. So or not all parallel to each other, parallel pairs. And so you gotta be careful. Rhombus, I'm probably butchering that a little bit. The idea, I think you have to have the definition of right angle in there too. So for both the rectangle and square. Otherwise, you're getting parallelograms and a rhombus in there too. So a little bit sloppy. Probably should have thought that through before I came up with it for an example. But the idea here is that a function will classify as a relation, but not all relations will classify as functions. So it's like the idea of function fits is a specific set of the overall idea of relations. So in this particular kind of realm of stuff that we're talking about, there is a very specific rule that's written down here. In the relationship that we're talking about that we are going to classify as a function, there is exactly one element in the range that is related to each domain value. Only one. Not two, not three, only one. So probably the best way to go about kind of identifying functions or not is to see if we can apply that definition to a function recognition quiz. So again, just kind of by telling you again, each element in the domain is related to exactly one element in the range. So first thing you have to do is say domain range. And so everything that's in the domain is relating to exactly one element in the range. So what I want you to do is take a look at these three examples and maybe pause, or if you're really fast, pick to yourself and say which one of these three or which ones of these three represent functions. A represents a function. Every one of the four elements in the domain are related to exactly one element in the range. B, each one of the four elements in the domain is related to exactly one element in the range. Now you might say, but it's related to the same one. That doesn't matter actually. For each element that you have in the domain, there's the one. The one can only be a 3. That's the only relation that's given. The 2 can only become a 3. The 3 can only become a 5. And the 4 can only become a 5. If I tell you I gave you a 3 and it told you to do this relation, there's only one result. You get a 5. You don't have to worry about it. You don't have to question whether it's going to be this or that. It is what it is. So that's what we call a function. If I give you a value, you kick back the same number every time because there's no choice that needs to be made. Part C. There are 4 elements in the domain. This is not a function, however, only because of what happens when we have a 1. So when you have a 1, I pass you the 1, and you get to, if you're the person that's doing the function or doing the relation in this case, I give you a 1, and you might decide to give me back a 3. You might decide to give me back a 5. You get to choose. As soon as that kind of choice has to be made, well, it could have been this, or it could have been this. That's not a function anymore. So this is a relation, not a function. So function, relation in terms of those ones. A and B are functions. Many times when dealing with functions or relations are given 2 sets of elements and the relationship between them, but we're not told what should be the domain and what should be the range. So this is just a lot of times with word problems when we're thinking about something that actually has some context to it. We're not necessarily sure which one should be which, domain, range, listed first, listed second, when you're doing your ordered pairs. So this is a discussion of dependent variables versus independent variables. It is how it sounds. If something is a dependent variable, it depends on the other one. If something is independent, then it does not depend on the other one. It sounds very clear-cut, but it's a lot more wishy-washy than it seems like it should be. So for instance, if I take the example of, we're going to say you have a part-time job, pays $12 per hour. We're going to track time worked, T in hours, as well as pay, P in dollars. Which one is the dependent variable? So the question is, does the amount of money that you get paid depend on the amount of hours that you have worked? Or does the amount of hours that you have worked depend on the amount of money that you have been paid? So you could probably get yourself flustered into a place where you feel like both those would be okay. But the more clear of those two options is you are going to work. At that point, you have probably not been paid yet. So what you're going to do is you are going to submit the number of hours that you have worked, or it's being tracked at your job, and in turn you are then going to receive pay for those number of hours. So the pay that you receive is dependent on the number of hours that you worked. You could maybe think of an idea where you have a contract of sorts where they're saying, well, we're going to give you $1,000 this month, but you need to work a certain amount of hours. So you're independently getting 1,000 and your number of hours is dependent on that amount of money that you've been given. A lot of cases you can talk yourself into corners that way by kind of rewording and thinking about these fringe cases. But most of the time, you want to go with the most clear kind of relationship between those two variables. If you feel like there is no most clear, and then I suppose you could pick either one as being the domain and either one as being the range. But for the most part, you should feel like there is a kind of like, oh, well, as the time passes through the day, that's independent. The temperature outside changes. So the time really doesn't care what temperature it is, but the temperature does change depending on the time of day. So you can, there'll be other examples like that you'll see. Most of the time, the more practice you get with it, the easier it is. You feel like you don't get as confused, dependent and independent. So again, the word depends is very helpful in tracking dependent versus independent variable. So this thing depends on the first thing. If it's dependent, then it is the range. If it is independent, it is the domain. So just going back here, this one, dependent, is going to be range. I probably could have switched the spots there. So if I did this instead, and we just say, I could have actually just put an I in there, right? Switch them around. So independent variable, domain, dependent variable, range. All right. So just to finish things off, a little bit of notation. So function notation is a special way to write algebra that goes along with this. Now, in the last example, if you're getting paid $12 per hour and the number of hours was T, time, and the amount of pay was P in dollars, like I put in the example, then the pay is just equal to 12 times the number of hours that you work, so 12T. P is equal to 12T. That is probably what you would consider normal algebraic notation for that relationship. If you want to tell people, you know that that's a function, so there's only one amount of money you can be paid for each number of hours that you could be working, then you can use what's called function notation. So function notation, as you can see right here, basically takes one of the variables, the dependent variable, and replaces it with what we call a function. So a function is a letter with a bracket. Well, the entire notation is a letter with a bracket beside it. So this is the function. And this part right here is what we call the argument. And the argument is the thing that is the independent variable in this case. So time is the independent variable. So what this says is that we have a function. It's a function, so we know right away, without anybody telling us what's on the right hand side there, we're dealing with a function. And there's a whole bunch of reasons why you want to know why you're dealing with a function, and we'll see some of those later on in this course. But knowing that you're dealing with a function allows you to do certain things and treat them in a certain way. So in this case, P of T is how I would read that out loud. So this is P of T. And that P of T means that I have some pay that is a dependent variable that is dependent on the independent variable of time. So pay is dependent on time, and I know that by seeing P of T in that particular expression. So P of T is equal to 12T. Now, sometimes you will come across algebraic expressions that have no context. So y is equal to 8x plus 1, for instance, is it is a linear function that we'll see later on. And so we don't really know what y is and we don't know what x is. Instead of using the label y, when we go to function notation, a lot of times we go to a specific part of the alphabet, actually. This is not entirely true, but F, G, and H are kind of like your go-tos. W is used sometimes, M and N are used sometimes, but just like A, B, and C are used as really common constants, and X, Y, and Z are used as really common variables, F, G, and H are kind of your go-to functions. So in this case, the function is F, and the function is acting on x's that are given to it. So the independent variable is an x. You give it to the function f, and it turns it into new values that will be y. So f of x is equal to 8x plus 1 is how we'll say that. I'll get you to take a look at some textbook questions that kind of get you to go back and forth. They're super simple to just go back and forth. There's not a whole lot going on. As you can tell, there's no math here. It's just being able to label what's going on in those particular cases. All right, so that's good for now. I hope that was helpful to you, and we are off and running into this idea of functions. Take care, folks.